Okay, let's see another example of a phase portrait. This time we're going to consider the system dx dt equal negative x plus 2y and dy dt equal negative 3y. Here the matrix is A equal negative 1, 2, 0, negative 3. We compute the trace. The trace of A is negative 4 and the determinant of A is negative 3 times negative 1 is positive 3. Then we have the characteristic equation is lambda squared minus the trace is minus negative 4, which is plus 4 lambda, plus the determinant plus 3 equals 0. We can solve this by factoring, and we have this time that the numbers are 3 and 1. That means that lambda is either negative 1 or lambda is equal negative 3. When lambda equal negative 1, to find the eigenvector, we have to think about this system, parentheses, negative 1 minus negative 1 minus lambda times x plus 2 times y equals 0. And here we have 0x plus negative 3 minus negative 1 times y equals 0. Let's see what equations are these. In this case we have, this is 0, we have 2y equals 0, and here we have negative 2y equals 0. Remember, we have to pick a solution that is different from 0. We cannot pick 0, 0, but then the first equation is telling us, please pick y equals 0. The second equation is telling us, please remember, pick y equals 0. What can we pick? Then in this case we can pick x equal 1 and y equal 0. We are not allowed to pick 0, 0. Okay, then this is the direction that goes with lambda equal negative 1. For lambda equal negative 3, to find the eigenvector, we do negative 1 minus negative 3 times x plus 2y equals 0. And the other case, the other equation is 0x plus d minus lambda minus negative 3 times y equals 0. What are these two equations? This equation is 2x plus 2y equals 0. And the second equation is just 0 equals 0. We need to solve the two equations. The second equation is always true. Then we just need to solve the first equation. We cannot pick 0, 0, but one possibility is to pick x equal 1 and y equal negative 1. Then we have our two eigenvectors. This is the eigenvector for this, and this is the eigenvector for that. Then to do the phase portrait, we do the origin, which is always an orbit on its own. And in this case, let's do the Cartesians just to draw the vectors. 1, 0 is here, and that means that this is one of the lines. And we label this with lambda equal negative 1. The other line is 1, negative 1. 1, negative 1. Then the line is the line that goes through that point, and the origin is like this. And we label that lambda equal negative 3. Let's erase this one because this is not part of the phase portrait. The direction of those lines, since the lambdas are negative, the direction goes toward the origin. The direction goes toward the origin. Now we have to do the other orbits. The other orbits are going to look like parabolas, but we need to decide which of the lines are the ones that are close to the orbit near the origin. And in order to do that, we just draw that in the real line, we do the two eigenvalues. This is 0. Here is negative 1, which is one of the eigenvalues. Negative 3, negative 1 and negative 3. Which one is closer to the origin? this one is closer to the origin. That means that this semi-line is the one that is making the roll of the x-axis, in the sense that the orbit is going to look like this, almost tangent to this line, far away is parallel to the other line. And the direction goes toward the origin. Here is almost tangent. The other one is like this. Far away is almost parallel. Near the origin is almost tangent to this line. The other one goes like this. And the other one goes like this. The other one goes like this. Remember that each one of these orbits, they stay in the quadrants. Okay, remember that in this case, this equilibrium point is called a sink, because the two eigenvalues are different and they are negative. And you can see like everything goes toward the origin. That's the reason it's called a sink. Okay, that's it for this example.